So up to this point, we've been talking very generally about energies and partition functions, but I'd like to do a sort of simplified example of how we can apply this to a given system. So let's imagine we have a system where we can have 4 different possible energies for the system. It could have 0 wave numbers of energy, everything's completely in the ground state. It could have 10 wave numbers of energy, 20 wave numbers of energy, or 30 wave numbers of energy. That's our total energy for the system. This is sort of like a not very realistic example, but it makes the calculations much simpler. And so what I'd like to do is say, okay, we have these 4 different possibilities. What is the value of Q? What is the partition function? And what is the probability of our system having the energy equal to energy 2, 20 wave numbers at a given temperature of 100 Kelvin? One thing we need to know that'll make this easier is that KB is equal to 0.695 wave numbers per Kelvin. So yeah, I like to use units of wave numbers because that's what I use in my research. You can do this all in joules as well. It's just you'll have 10 to the negative something large to be able to do it. Okay, so what is Q? Well, again, Q is we add up e to the minus beta times our energy. So e to the minus beta times E0 plus e to the minus beta times E1 plus e to the minus beta times E2 plus e to the minus beta times E3. Okay, and now we just need to plug in what is beta and what are the different energies, and that'll let us calculate Q. Okay, so our energy of, so our first term is going to be, so first of all, we can calculate beta, again, is 1 over kb times T. So we can plug in 1 over 0.695 wave numbers per Kelvin times 100 Kelvin. All right, calculate that real quick. Let me just pull up my calculator. I'm going to make my screen disappear. But we have 1 divided by 0.695 times 100. So beta is equal to 0.0144. We'll just round to 3/6. All right, and that has units of 1 over wave numbers, which will cancel with the energies that we're going to multiply by. Okay, so our first term is e to the minus 0.0144, 1 over wave numbers times 0 wave numbers. Okay, so that's going to be pretty straightforward. Plus e to the minus 0.0144, 1 over wave numbers times 10 wave numbers, plus e to the minus 0.0144 times 1 over wave numbers times 20 wave numbers, plus our final term, we're going to squeeze in down here, e to the minus 0.0144, 1 over wave numbers times 30 wave numbers. Okay, so now we need to go ahead and plug this in to our calculator, which I'll bring up again. So we'll have 4 terms. So we'll have our exp exponential of negative answer. Answer is the value of beta times 0. So that just gives us 1, plus exponent of negative answer times 10, plus exponent of negative answer times 20, plus exponential of negative beta times 30. Oh, forgot the times. Okay, and so we do that calculation, we get this value here, which is 3.27. So it's just, so our partition function is simply a number at the end of the day. It doesn't have units, and we will discuss in a little bit what this means. What does this number tell you about the system? The other thing we wanted to do was calculate what is, right, so that's our partition function at 100 Kelvin for this system. The other question is, what is our probability, right, P2? What's the probability that we have our system in state 2? So P2 is equal to e to the minus beta times E2 divided by Q, divided by our partition function. Okay, so that's going to be equal to e to the minus again, we have our same beta values, 0.0144, 1 over wave numbers. So the units cancel, times 20 wave numbers, which is the energy of state 2, divided by 3.27. All right, so let's go ahead and calculate that. Okay, we have exponential of negative 0.0144 times 20 divided by our previous result here. So that's equal to 0.23. So what that tells us is there is a 23% probability at 100 Kelvin that our system has an energy of 20 wave numbers. And so we would also have probabilities of all the other energies as well. Okay, so that's just a quick, somewhat practical, it's idealized example, but somewhat practical example of how you would actually calculate a partition function given some energies, possible energies for your system. Of course, a real world example, you wouldn't have just 4 possible energies and they wouldn't be nice and evenly spaced like this. But this gives you an idea of sort of, we have these abstract equations, like what does the sum mean? What do the E values mean? And this is an example. And we'll do some more examples of this when we meet together in class.